Our Gibbs free energy equation becomes very important to predict whether or not a reaction will happen. And there are, we will see, two competing forces, the enthalpy and the entropy, competing to make a reaction delta G favorable or unfavorable. We know that the exothermic delta H's are favorable. The ones that require energy to go in, heat energy, are not favorable. We also know that positive entropies are favorable because you're getting things to spread out and there's higher probabilities of that happening. So those drive the reaction. And just kind of there, if you see those conditions that are favorable and how they combine, chemically, we can use those to predict will the reaction be favorable or not just by the concepts. So in case one, if we have two favorable conditions, exothermic and a positive entropy, we will say that this is always favorable. It's driven by both entropy and the entropy and enthalpy. In the second case, we see that neither one of those conditions is favorable. They both require energy from the outside. So neither one of them is going to drive the reaction. And of course, I can't spell. Neither one is going to do that. So that type of reaction is never going to happen because it requires too much energy from the outside. It's not going to happen on its own. Here we've got two competing cases then. In an exothermic reaction with more structured entropy, this one will be driven by the enthalpy, so delta H will drive this reaction. And in the bottom one, if this reaction is going to work, it's because delta S would be driving the reaction. Okay? We can also do this. So this is a chemical look that we just talked about. We can also do this mathematically and see how these would affect the delta G. We know that delta G being positive is delta G being negative is favorable. If the energy is being released, the Gibbs free energy is being released, that is a good thing. So mathematically, we have a delta H minus delta S. And mathematically, how will that affect delta G? We know the temperatures are always positive in the Kelvin scale, so we have delta H competing with delta S. In my first scenario, if I have negative delta H minus a positive delta S, we will say this is always, delta G is always negative. That means it is always favorable. Okay. The second case, if I have a positive delta H minus a negative delta S, that's going to be a positive delta S. When I combine these, there is no way to get anything but a positive delta G. Delta G will always be positive, which means that reaction is never favorable. It will not happen on its own without outside intervention. The next two cases, though, are a little confusing because they compete with one another. In this one, I have a favorable negative delta H, but minus a negative. I've got a fighting factor here with the entropy. That's going to be a positive term. So I've got a negative term and a positive term. Which one wins? So now it actually depends on the temperature. If I have a high temperature, that makes the entropy more important. If I have a low temperature, it makes this less important and the enthalpy takes over. So the temperature has a deciding factor in these two bottom scenarios. Okay, so at a low temperature, At a low temperature, the entropy is not as important, and the entropy is not favorable in this case, which means delta G will be negative, because now the enthalpy takes over. But at a high temperature, delta S becomes more important. At a high temperature, this term is bigger than this term, so delta S takes over, and my delta G becomes positive because my entropy drives that to be a positive number. And in the other case, it's reversed. In a higher temperature, the entropy is more important. Well, in this case, the entropy is favorable, so a higher temperature actually will make this reaction happen, and the delta G will be negative in that case. But at low temperatures, delta G will be positive because the enthalpy is more important at the low temperatures. And these two conditions here, when we have temperature dependence on our reaction, if you think about any phase change, phase changes are very common in these two categories. There is a temperature threshold. Above that temperature, you get one phase change, and below it, you get the reverse. And you don't have water boil below, freezing point. So that's kind of what's happening in these other two states. The temperature makes different terms important, and they compete with one another. So now we want to make some predictive properties on, or predictive signs for these following properties. So water freezing, that's water going from a liquid to a solid state. Energy has to be lost. That is an exothermic process. It is also becoming more ordered. So that's a negative process also. The entropy is going down. And delta G, we need some context here, at 25 degrees, delta G in this case, does water freeze at 25 degrees? The answer is no. Delta G is going to be positive at 25 degrees. Carbon dioxide subliming. That's an endothermic process. Energy has to go in to turn it into a gas and break the intermolecular forces. It is also a very entropic process. You get a lot of gas generated. And at 25 degrees, this does happen, so delta G must be negative. And in each case with 25 degrees, again, we're getting a threshold here. We can see that the entropy must be driving this one at 25 degrees because it's not happening. Likewise, if the CO2 is subliming at 25 degrees, and it is happening, the entropy is also driving this one. That's causing it to happen at 25 degrees. Okay, sodium chloride dissolving. This one we would have to look up. It actually has a positive delta H. It's slightly endothermic, but the entropy is also huge. Because you've got solid particles going into aqueous particles. So that's actually, and we know that that happens at 25 degrees. Salt dissolves in water. So delta G must be negative there. We're using kind of common knowledge to figure out delta G's because all of these are temperature dependent and they're being driven by different processes. So we're just using some common knowledge to figure out if these will happen. Wood burning, delta H, very negative, exothermic. Lots of gas being generated. I've got two favorable terms here. Let me get the highlighter out. Very favorable delta H and delta G. Here I've just got one favorable term driving it. That means that this will always be negative. Got to switch back and forth. So delta G is always going to be negative because both of those are favorable. And this is a good reminder that wood does not just catch fire by itself. thermodynamics, even though this is always a favorable process and will always happen, this has nothing to do with kinetics and how fast it happens. You still have to overcome an activation energy to start this reaction, but once it starts, it will just go on its own because it is a favorable reaction with exothermic energy states and very positive entropic gas being generated. Okay, for this problem, we just plug them in and we're just calculating delta G and trying to determine if it is spontaneous or not. Spontaneous, remember, we're using that word. You're going to see it in the book. We do not want to use spontaneous or not spontaneous. We are going to say favorable or not favorable. So we want to change those words when we see them in the book. Okay, thermodynamically favorable or not, because this has nothing to do with kinetics. So my delta G equation, delta H minus T delta S. Temperatures need to be in Kelvin. They all are. That's good. We do not have the alignment of joules and kilojoules, so we have to change these. Delta G's are typically going to register in the kilojoule scale, so it's better to change the entropies and adjust everything into the kilojoule scale. What we're going to get, you guys can plug these into an equation. Delta G for all of these, it's going to come out to, this one's plus 1 kilojoules per reaction. The next one is minus 5 plus 85. Minus 1 and minus 85. Okay, and will they happen? The positive ones are no's, and the negative ones are yeses. They are favorable. If you have the right kinetics and activation energies, these will happen on their own. They are favorable energy states. Okay, now we can take this a little bit further here, and these are just math calculations, but then we could actually say, okay, look at these 5 choices. Which one of them represents the same balanced equation? Which one represents the same system? And the answer to that would be, even though all these numbers look similar, we would see that they have to have the same thermodynamic properties in order to be the same system. So we see that A and B both have positive 40 delta H's and positive 300. These are most likely the same balanced equation, but 2 different temperatures. And we can see there's a temperature where it works and a temperature where it doesn't. And there's probably a threshold somewhere in the middle there, which we'll talk about, where delta G equals 0. None of the other ones match up quite like that, so these would all represent different balanced equations, different thermodynamic reactions. But A and B are very similar, and this is the same equation with 2 different temperature thresholds. So what is the minimum temperature this reaction needs to take place? You're going to see this phrase a lot, minimum temperature or maximum temperature. Any delta G equation that has a temperature dependence when only one of the 2 terms is favorable and they compete against one another, that means the temperature is going to determine there's a temperature above where it'll happen or not, and then below it'll be different. Any phase change is going to do this. So whether it says minimum or maximum temperature, and you see that this happens, what they're telling you here, there's some very important information you need. There is a temperature where delta G equals 0. And this makes a lot of sense. Okay? If we had a number line and there is a threshold and we say delta G's are, if they're negative, it's favorable. And if delta G is positive, it is not favorable. In order to go from positive to negative, there is a 0 point where it flips, and that is a threshold temperature. So we will say minimum temperature or the maximum temperature. It's just the temperature where it flips, and that is where delta G equals 0. Okay, so we can use that then because they're not giving you those numbers. So 0, we just plug it into the Gibbs equation, equals 44 kilojoules. Let's put the units in so we can see them. Minus temperature times delta S, and we're going to make that into kilojoules as well. 0.119 kilojoules per Kelvin, and then the Kelvin temperatures there will cancel out. And we can solve that temperature is 370 Kelvin. So that is the temperature, and we can see with sig figs it's an estimation. We kind of already knew what it was with water. It's about 100, 373. But sig figs there, it's an approximation that we get a temperature that the phase change will happen. Those are boiling points, those are melting points, vaporization points. There's a lot of words they can use them, but the important part there is to recognize that delta G is 0 during those points at that temperature threshold. For these balanced equations, we want to predict the sign of delta S. Now, we've known that delta S has to do with positional probabilities, solids, liquids, and gases. And when we look at a balanced equation, we can represent that. The most obvious way is by looking at the gas particles. If there's a tie, then you can start going down the line. Aqueous particles will work the same way in an aqueous system. But then you go to liquids and solids would be last because they're very insignificant compared to gases. So predict the sign of delta S. If we look at the gas particles for this first reaction, we have 0 on the left, and we have 5 moles of gas on the right. So delta S for this first balanced equation, the system is going to be positive. We're getting more entropy. Okay. The system is always the balanced equation. The second equation here, we've got no gas on the left, and we've got 1 gas on the right, 1 mole of gas. So delta S here again is positive. And this third one, I suppose I should have chosen different examples. 1 mole of gas on the left and 2 moles of gas on the right. Delta S will again be positive. If we're making more gas, we get positive. Same thing with aqueous. If we get more aqueous, it'll be positive. If it's reversed, then we would change the sign and it would be less. But we can predict delta S by looking at the phases and the coefficients. These are our famous summation equations that you just need to watch out for. You use your book in the appendix to calculate products minus reactants times their coefficients, and you can set all of these up using that equation. So the first one, we would say the entropy, because they all have an absolute entropy of the system, is going to be equal to 2, and I always use the big brackets and the little ones. It doesn't matter what we have in there. We want 2 NO2 gases. That's my products, minus, we've got 1 N2O4. Right? My second one, delta S, is going to be 2 Fe solids plus 1 aluminum oxide solid. All of that minus, big brackets again, this is where people often lose their signs, 1 iron oxide plus, and that negative sign needs to get distributed, so you watch out for that, 2 aluminum solids. So if you just watch out for your brackets, you plug all these numbers in, show all your work, you should be in pretty good shape for these. The first one is going to come out, if you look these up and plug them in, to 176 joules per Kelvin. The second one is going to come out to negative 41. And the third one, if you plug those in, is going to be 181 joules per Kelvin. Okay, so this is it's the hardest, easiest equation in chemistry. Show all of your work. It's good to write these out. It's good to plug the numbers in directly, and simplify them. Don't try to do it all in your calculator at the same time. There's a lot of parentheses. So just be slow, be careful, and you should get these. These should be good points.